we'll get a better turnout tomorrow.
Well, I've got another one to do tomorrow as well. So. Mm-hmm. Okay. Want to welcome everybody here. This is great. Seriously, I love this campus. We've worked here before. We came in a while back and worked the InSight mission from here, and that was exciting. That was really just we spent several days up here and got to meet a lot of great people. And it's a good area too. I spent this is about my 5th trip here, so I don't know that I've eaten in all the good places, but there's several good places around. Come on in, have a seat. I'm Brian Mitchell. I have been with NASA almost 34 years now, all at the same center. I'm from Marshall Space Flight Center in Huntsville, Alabama. I've worked on a little bit of everything. When I got there, I started in shuttle payloads, and I worked space station. We ended up going over to the PMPO, which is the Planetary Missions Program Office, which is where most of these programs that you're seeing lately are managed out of. So that's what I do now, and I'm the communications manager there, and they send me around. They couldn't shut me up, so they sent me around to start talking to people. So that's what I do. Anyway, so that's the Planetary Missions Program Office. What we're going to do, we're going to talk a little bit about the office itself. We're going to talk about what we do, maybe a little bit about who we are. You'll get to meet some of the mission managers, that sort of thing, and then we can open it up. We can talk to, you got any questions at all. I may not have an answer. I can get an answer, so we can go from there if you want. Let's see. All right, who we are. By the way, does anybody know what body that is? I didn't think. All right, it's an ice moon. That's Europa. This is our office at Marshall. There's no test or anything like that. That's the reason it's all muted and everything. I just wanted to give some idea about the size of our office. Everybody has a job. I'm up here under communication and outreach. My support person is Stephanie Henry, who is over in another building right now, where all the exhibiting things are set up. So we'll be here for a couple of days. We've got a lot of really good, really interesting speakers set up. Lori Glaze will be talking tonight, I think, and from 6 till 7. And she's all of our boss. So she is the head of Planetary. So pretty much everything that we do goes through Lori right now. So anyway, what we do, we have 3 pieces to our program office. We have the Discovery program, the New Frontiers program, and the Solar System Exploration program. They're divided like that because they're divided by the frequency of the mission and basically a cost cap on the mission. And there's different hurdles that you have to go through in order to qualify for these things. So but all 3 of them together keeps us pretty busy. We do fly a lot of the Discovery missions, which you'll see. We're going to go into some detail here in a minute about the different missions in these categories. And anybody gets bored, let me know. Anybody got a question, stop me, and I'll do what I can. These are some of the missions in our office right now. That's a fairly long list, but it's some of them are current. So there's some future missions on here, and some of them are. We try to pull off the past missions. Things like, we've had missions in Mercury that have just timed out, and we don't say crash. They deorbited, into Mercury, resolved themselves into piles of metal filings. But anyway, this just gives an idea of the different places that we are in our program office right now and the different types of missions that we have. InSight down here under Mars, launched out of Vandenberg a couple of years ago. That was That was the one I was talking about just a little while ago. Now this chart I had never seen until a couple of weeks ago, and I really liked this chart. It's the science fleet, our currently operating science fleet, and I had no idea that we had that many programs and projects going at any one time. We don't, out of our office, we don't do really any of the Earth satellites. We don't do any of the solar satellites. We do some Martian satellites, but we do everything else. So looking at this chart, I kind of was impressed myself. So anyway, I thought I would include that. The Discovery program, which was the first on the list. Insight, that's the one that launched out of here a while back. That was a beautiful launch. I wish I could have seen it. The fog came in, and the fog was supposed to be up to about 600 feet, and it came in at about 800 feet, and I was about 650 feet. So it sounded great. I never got to actually see it. That did land on Mars. They had some difficulty getting the penetrator to penetrate. They still got some really good science out of it. They're still operating that. They're still working workarounds on what can we get out of it if we weren't able to get the data that we were looking for. What data can we get from it? So we're still chugging along on that one. And Brad's out of our office, and he's heading that up for us. That was 3 years ago. Yeah, about 3 years ago. Yeah, sure.
When I was in junior high, I watched the live stream of Curiosity. Is that still running?
Curiosity rover. It's on Mars. It's not one out of our office. We have an office that's strictly Martian, with a couple of exceptions. You know, it's a little confusing, but most of those are run out of JPL. The Mars Exploration Office is run out of JPL, so they build the rovers and operate them. So, but yes, that was definitely one of them. All right, that was that launch. That's the part I didn't get to see. I really wish I had. I was a couple of hundred feet below those clouds, so I missed it. But like I said, it sounded great. Okay, LRO. LRO was actually one of my first missions to work in this job. LRO, the Lunar Reconnaissance Orbiter, is still orbiting the moon. It's probably one of the, in my opinion, one of the more successful missions that we've ever had. Like I said, it's already collected more data than all the other planetary missions combined. Before we had that, you know, we had Earth-based observatories, we had footage from Apollo, we had that sort of thing. But with this, you could pick this table out on the lunar surface. It's really interesting. If you go online, you go to any of the NASA websites and look this stuff up, you can see tracks from the lunar rovers. You can see boot tracks in the soil from the photographs that we have because of this thing. So we've been able to map the surface so well now that this is really, really going to be an asset to us as we go back. And we are going back, by the way. The Lucy mission, Sherry runs that one, and it just launched. I mean, it launched last month, actually, and it's going to study the Trojan moons around Jupiter. I don't know how many science students do we have in here? Are you math, engineer, any of the physics or physical sciences? Okay, we got one. Great, that's going to make it a lot easier on me. All right, so anyway, so Trojan moons are moons that are actually captured in a certain orbit, and they orbit with Jupiter. They don't orbit in the asteroid belt itself. They orbit with the planet itself, and they're considered to be some of the oldest bodies, the most pristine of all the asteroids, because they haven't been in the asteroid belt just ramming into each other for eons. So this mission is to go study those. So we should learn a lot about the early formation of these things. Come on in, guys. P-Sampler, we partner with several other agencies. We partner with the European Space Agency. We partner with JAXA in Japan. If they have a mission going and they have some margin for payload, then we'll help them. They help us. So we put different instruments on their spacecraft, and sometimes we allow them to put instruments on our spacecraft too. And this is one of those. It's going to study Martian moons, specifically Phobos and it says so on here somewhere. But anyway, it's another one of those that's going to study the Martian moons. This particular spacecraft, we've got more than one experiment on. Psyche. I don't know if anybody's heard anything about Psyche. Psyche is actually the name of an all-metal asteroid. It is a huge, huge, huge metal asteroid out there that we've identified. And we don't know why it's there. We don't know if it was the core of a planet and the exterior of the planet was bombarded and eroded away. But we've got a way to determine which came first. The core of a planet will decay in a certain way. It decays from the inside out. And if this was just a natural decaying planet, it will be decayed from the inside out. If it was obliterated, it will decay from the outside in, and we'll be able to tell that once we get in orbit for this. And it launches. I think it's got a launch coming up next year. I think it is next August. Strofio is another one of those missions that we partnered with. We partnered with the Bepi-Colombo mission with ESA, the European Space Agency, and it's the next step in going back to Mercury. So we'll go back to Mercury because our previous spacecraft, like I said, deorbited several years ago into Mercury's surface, and by the time it got there, by the time it completed its mission, I mean, it was older technology. I mean, you think of how fast technology changes now. And one of the missions that I brought up earlier, the New Horizons mission, I mentioned that when it launched, Pluto was a planet, and it took 9 years to get there. So you've got 9-year-old technology flying past a planet. And if you could just snap your fingers and upgrade all that technology, we could have gotten a lot more information out of it. So, okay. SIMPLEX, I believe this is another one that it looks a lot like, I swear that picture looks like LRO, but it's not. But this is another one of those partnering missions that we do where you'll have JAXA or somebody like that build the spacecraft, and we put some of our technology on it, our demonstrator technology. Things that it's not worth us necessarily putting an entire mission together, an entire flight together, but we want to be able to prove or disprove a certain type of technology. New Frontiers. Like I said, there's one of 3 here, and New Frontiers is a little bit more expensive missions. There are fewer in between. It takes longer to build them and plan and build them. And have you heard of Juno? Anybody heard of Juno? The Juno mission is a mission that's been it's been in orbit. I want to say it's been in orbit around Jupiter, but it's in orbit more than just Jupiter. It has a really long elliptical orbit because Jupiter is so radioactive. If you just put something in orbit around Jupiter, it's going to fry. And so what we do is just scoot past it really fast, make a bunch of pictures, make a bunch of studies, make a bunch of measurements, and then fly on past it. So we don't spend too much time in that radiation. And it's done several of those passes. And the photography from this thing has just been amazing. The things that we've learned about the surface that we had no idea before. And it's getting close to the end of its life, but we're still getting some really good stuff from that one. This is the New Horizon one that I told you about that flew past Pluto. And it was interesting, even 7 years into this mission, the best photograph I had of Pluto was a blob. It was just a blob. And I'm going around trying to explain what we're doing with this mission, and I've got this picture of a blob, for Pluto. So this is the difference that we have now in the photograph of the surface. And we know we didn't stop, we didn't go into orbit, we were going way too fast to stop. That's another question that we were talking about earlier with some of the other people that were in here. It's the same principle. It's well, how long does it take to get to the moon? I said, well, it depends on whether you want to stop. If you want to stop, it takes a long time because you have to go slow enough for the gravity of whatever body it is to capture your spacecraft. If you just want to slide past it, you can slide past it in no time. The difference is 4 days to the moon if you want to stop at the moon, 4 hours if you don't. So it's a significant difference. So this thing was going so fast that there's no way for this small planetary body to capture it in orbit. So you just made all the photographs and studies you can as it went by. And then we have redirected it. It's out past Pluto now. It's still functioning. It has a little bit of margin in fuel. We've been able to redirect it to other larger Kuiper Belt objects. And so we'll get more information out of it. We'll get to study more stuff out of that spacecraft. Dragonfly. Now this is one of my favorites right here. Dragonfly. It's a drone. We're gonna send this drone to Titan, which is the largest moon around Saturn. It has enough of an atmosphere that it will support a drone, and so we will be able to land and study places, fly to other places and study those, and move this around until it gets probably covered in dust, and it won't be able to recharge its batteries after a while. But that's just too cool right there. I like that one a lot. That's one of my favorite missions, and I'm thinking I had talked about retiring, but I may have to hang around for this one. I just kind of want to see what goes on with this. It's early in the planning stages right now. I mean, I don't know that they have a ride yet, but they're talking about that happening within the next 3 years. So, stay tuned. OSIRIS-REX. OREX has already flown. Surveyor is here. She's helping us work the exhibiting area over there this week. She's the mission manager for that. That's an interesting mission in that we are bringing back a sample return from this particular asteroid. It did not land on the asteroid. It just sort of kissed the surface of it. It had a robotic arm extend from it. It got close enough to the surface where the arm touched the surface. It blew out all this gas in a pattern that blew a lot of debris into a catch basin, and then the catch basin closed up and it goes into a capsule on top of the spacecraft, and the spacecraft comes back. And we were a little worried at first because we noticed when we closed the capsule, some of the sample fell out, and we thought, oh, did we just lose our sample? How do we find out if we're going to bring back an empty capsule? And so it took a while, but we figured out that there's enough mass in there that the reason some fell out is because we got so much more than we had planned to get. And so some of it fell out as we were closing it up. But no, that thing should be jam-packed full of stuff. So it'll be back. It launched in 2016. I think it's supposed to be back in about 2 more years. It's finished with what it's doing, but you got to wait for the right launch window for it to come back.
Where does it come back to?
It will fly back into the Earth's atmosphere, and I believe this one lands in, I forget which desert. But we've done that before. We've had that technology. One of the other missions that we had flew through a tail of a comet and collected a bunch of comet dust and brought that back, and it landed in a desert. And we were able to open it up and get lots of particles and stuff from that. So, but anyway, different type of mission again. Oh, sorry. Yes, sir. Mm-hmm.
What determines if it's the
Right launch window will have to do with the position of the planet itself, the position of our planet, the position of any other planets that it's going to get a gravity assist from. Yeah, because a lot of our missions use the gravity from other planets to pick up speed and direction. You don't just fly to a planet. You fly to a point where that planet will be at a certain time. And it's amazing to me how they're able to calculate, okay, the gravity from Mars is going to add so many kilometers per hour, and we're going to come out of that gravity at this angle. We can give a little nudge with an engine, and it'll put us in the right trajectory to go around, say, Jupiter, and do the same thing. We're going to pick up speed when we go around Jupiter, and it's going to sling us out this way. We do a couple of little adjustments, and then the next thing you know, we're at Pluto. You know, so you've got to pick those times to do that. To carry enough fuel to just ignore all of that and just fly a mission straight back would be very cost prohibitive. I mean, just to get that much fuel off the ground, you know, to use. Yeah. So you find that launch window, you know, where all the stars line up. So, yeah. The DART mission, which is why we're all here. Clayton has that. Clayton is also here. The DART mission, there will be several people talking about it all week. So I won't go into a lot of detail about it. I have another presentation here if anybody really wants to see it. It's basically a ballistic mission. It's not the most complex of missions for us, but it's the first of its kind. It's, and in my personal opinion, long overdue. We have a relatively new office within NASA called Planetary Defense. This will be the first of the planetary defense missions designed to learn what we have available, what methods that we can determine in order to mitigate being hit by, you know, a large body, because we have a lot of near-Earth close encounters. By close, I mean they're still pretty far away. We track a lot. Sometimes, depending on which direction they come from, we don't see them, you know, till it's kind of late. And we need to be able to do something about that. And this is the first of those. And we're going to push this spacecraft out there. There's Didymos A and B. And Didymos B is basically a moon going around Didymos A. And so instead of just hitting an asteroid in the asteroid belt that's not giving us a problem and maybe deflecting it to some area that it might potentially give us a problem, even though that risk is extremely low, why take it at all? So we found a small asteroid that's orbiting another asteroid. And so if we can just bump it a little bit, just to show that, yeah, we can redirect this and change its orbit around this other asteroid. It's still going to follow that asteroid. So it's not anything that's going to turn into something dangerous for us. But it's a baby step, but it's a step, you know. What do we do next? I don't really know. There's been some interesting ideas out there that are just spooky. But, yes, sir.
Could you possibly, like, with this DART mission, if it was successful and
Mhm.
Could you hit, like, change the orbit of an asteroid to hit another asteroid to change that orbit? The orbit of that
Well,
asteroid?
theoretically, yes, but again, the mass that it would take to do that would probably be something really crazy. Yes, sir.
How much does the dart being too slim in the asteroid weigh?
How much does it weigh? I've got those on some of the other charts. It's not particularly heavy. We're not relying on the mass so much as we are the speed of it, which is, again, mass is expensive. Mass takes a lot of fuel. Speed doesn't take as much fuel if you use those gravity assists like you can. And so you can pick up a lot of speed doing that with very little fuel. And that's what we rely on. It's not so much the size of the spacecraft, but how fast can we make it hit it. All right, so that's, I mean, if you obviously if you used more mass and you had it going the same speed, you could get bigger results from it. But like I said, I can pull up a chart in a minute and tell you the mass of that spacecraft. But it's the mass of that spacecraft is almost a secondary kind of thing to the speed that it's going to be going. Sir.
I have another question about the DART mission. So, you guys at NASA predict that it's going to change the orbit of the
Of Didymos B.
5803
Yeah.
asteroid. Do you think that's going to change the orbit of the binary asteroid?
I don't think that we're going to affect it enough to do anything like that. Now there's two ways we're going to measure, you didn't even ask this part, but there's two ways we're going to measure the effects of this impact. One, there's a CubeSat flying with this thing that should give us some measurements as well. It won't actually crash into the surface. It will detach, and then it will watch. Hmm? Oh, the CubeSat. I don't remember the name of it, but yeah. There's going to be tons of information around here about it. And the other way is just ground-based observations. We should be able to tell with ground-based observations that if we adjusted that orbit just the slightest bit. So, hey, telescopes have gotten a lot better. So, but, okay. So, like I said, we can go into more DART information in a little bit, time permitting, if you want. Europa Clipper and Europa Lander, that's a biggie right there. Scott was the mission manager for OSIRIS-REX when it launched, and then he got put into this one. This is probably one of the biggest and more complex missions that we've done in quite a while. None of them are easy. They seem easy sometimes, but none of them are easy. You know, people talk about, well, we go to Mars all the time. You know, that's easy for us now. There's nothing easy about going to Mars. But the Europa Clipper, I don't know if anybody knows anything about it or not, but it's going to go check out Europa, obviously. And one of the reasons we want to check out Europa is because we have a pretty good idea that Europa, even though it is an ice-covered planet, has a warm ocean underneath it with a rocky planet underneath that warm ocean. And there's not a piece of ocean on this planet. The hottest or the coldest piece of ocean on this planet has life. And so if we're going to find something, not just maybe fossils of where there used to be some microbial life or something like that, but actually find something swimming around, ever tiny small it may be, or floating around or whatever, that's a good place to look. That's a really good place to look. Now, the question is, what do? You have a penetrator, what do? You find a thin place in the ice. Well, lucky us, there are a few cracks in the ice. And every once in a while, one of these ice plates will crack, and it will spew ocean out ice crystals from the ocean out. So what we want to do is fly through those. We want to fly through those ice crystals and see what we can find, because that's just hours earlier was ocean, and hopefully it contains something. Yeah, yeah, you can see. Yeah, they're miles above the surface. Yeah.
How big is Jupiter's moon Europa compared to Earth?
Europa is huge. It's not the size of the Earth, but it's comparable. I mean, if it was off somewhere else and had cleared its own path, you could probably call it a planet. It's big. Yeah, this one, that's an exciting mission right there, and that launch is planned for 2025. Again, it's a very complicated mission. It may be one of the first missions that flies on our new SLS spacecraft. So, Space Launch System spacecraft. We're building an entirely new. It's like the replacement for Apollo. They would shoot me if I put it that way too many times, because it's not Apollo. But it would be basically our replacement for a heavy lift vehicle using more modern technology. It looks like it's kind of like a shuttle, but it's a lot bigger, it's a lot taller, and it has a capsule on top of it. And our first test launch, I think, is in February. There won't be anybody in the capsule, but it'll all be mated together. Most of it is already mated together at KSC, and they're prepping it for flight. Right. Absolutely. Yep. So the actual launch for this would be 2025. We would have several other launches with that rocket before then. Most of the rockets we use, DART's using a Falcon 9 out of here. We use a lot of Atlas rockets out of the Cape, that sort of stuff. Well, this is like, it's the great granddaddy of those. So, I mean, I don't know if you've seen a picture of it or not, but it's two really big solid rocket boosters. It's got a big orange tank in the middle of it, just like the space shuttle did, but it's got a stack on top of it of boosters and a capsule. And the capsule holds a lot more people than the 3 people that we used to have in our Apollo capsules. So that's another cool mission. Now, it's going to be complicated right now. I can't say that there's really been any serious problems with it or anything like that, but there's a lot of people involved in that. So launch slips do occur, but
Can I ask you a personal question?
of course.
Dragonfly or this one?
Ooh, 2 different things. Dragonfly is just something to kind of pass the time with while this thing is being made, I think. So it's Dragonfly is so interesting to me just because it's the first of its kind. This one is not really the first of its kind, but it's the first of its destination. We have flown spacecraft by Europa and studied it that way, but we've never done anything to study the surface or anything coming out of the surface of it. So, this is what we would consider a flagship mission. It's one of our bigger ones. Obviously, cost more, longer to plan, longer to construct. Yeah. Mm-hmm. Juice. Oh, sorry. Thought you were raising your hand back there. Jimmy. Another one of our partnership meetings, our launches, European Space Agency again. Study Jupiter's moons. We're studying Jupiter with Juno, and some of the things that we've learned from that brings up a lot of questions about Jupiter's moons. So it's like the more we learn, the more we need to learn. And so this is going to do that. And I don't have a launch date on it yet, but that kind of depends sometimes on our partners. Most of the time, we don't have any problems with them. Sometimes we have more problems with our own stuff. So it's not like the European Space Agency can't put hardware together or anything like that. They're quite good at it. They're very good at it. They know what they're doing. And same with JAXA, the Japanese. Surveyor, that's again Sove, or Sove, the G's silent on her name. I don't know as much about this one. This one's actually fairly new to our program office. It's mostly to map some of those near-Earth asteroids that we just talked about earlier that we may not be able to see, but could pose some potential danger to us at some point. And so this could help us find targets for us to have more DART-type missions for, and especially if we learn what we hope to learn from the DART mission. All right, that was the end of the slides on my program, but I can talk about any questions. I can go into a DART presentation if you want me to. One of the things that surprised me most about the DART presentation that I found and I was going through, it's not actually my presentation, but the size of Didymos B and Didymos A. Didymos B is tiny. It's do what?
Around 530.
Yeah, about 530 feet. Yeah, something like that, which is surprisingly small. But then again, if you're going to impact it with what's left of a Falcon 9 rocket, you know, because the whole Falcon 9 rocket won't make it that far. You're going to drop off pieces of it. So it can't be too large, you know, for this. So, but we should learn a lot from this. And the launch, right now the weather looks great. Just depends on the fog. That fog. That fog, that fog, that fog. But right now it's showing clear, or at least clear skies anyway, for the launch. And launch tomorrow night. And what's that, like 10:20? Something like that tomorrow night. Anybody going to get to go see it? Great, great. Of course, I'm sure being next door to Vandenberg, you guys see launches all the time, so no biggie.
But I have a question. So NASA's got, you know, bases and offices and things all over. I know you have a presence at Vandenberg.
Right.
Do you see expansion of that in the future?
Possibly, because in the 33 years that I've been there, we've only launched twice out of Vandenberg, and Vandenberg is proving to be more of an asset than I think it was thought of before for these launches. And so I would see us flying more out of here. I've only flown or supported launches from 3 sites, and Vandenberg, 2 out of Vandenberg, a dozen or so out of KSC, and 1 from Wallops. We flew 1 from Wallops, the Laddie mission, out of Wallops, and I mean that worked out well. Although that place, they don't do very big launches. They do a lot of sounding rockets, things like that, and they were not prepared at all for a mission to the moon. So we started that process months and months and months ahead of time, because that's what I do now. I go to these places early and start talking about the logistics and find the people that we need to talk to and explain to them what's going to happen, how many people are going to actually probably show up for these things, just the logistics of putting one of these things together, everything from crowd control, traffic control, signage, and usually the first time you just get this doe in the headlight look, and it's okay. We'll walk you through it. We'll walk you through it. We've done it before, and they always turn out well. So, yes, sir.
I had a question on the asteroid that you flew and gathered up some samples.
And the comet. Oh no. You're talking about OSIRIS-REX. Sorry.
Well, I'm just wondering if it would be more efficient to send along some test apparatus to do the testing instead of trying to bring it all the way back years and land it and everything?
You can do a certain amount of testing there, but to be able to slice things apart, and which is, I mean, it's invaluable to actually have a piece of something that you can get under microscopes. And I mean, you can tell, I mean, you can hit it with, and get the major pieces of it with a spectrographically, you can get most of that information. But to be able to slice one of them and look at it that way, find a pristine example of it that's not been affected by heat or anything else around it, tells you a lot. So getting those pieces back will tell us more than if we had just brought some instruments. I mean, if we had brought, a lab, basically, there, and to be able to do some of that, but that would have put it in a whole different class of mission, and it would have made it so complicated that we may or may not have even gotten permission to do it.
Aren't they doing a similar thing on the surface of Mars where they're actually doing an analysis there, sending back the data rather than bring back the samples?
They are, but we've also got missions on the books now to bring back samples of those. One of the reasons that we do the rovers on the Mars is to find interesting places that we might want to bring samples back. Okay, so we can do a lot of preliminary studies of what we see, but it's not going to be the same as if you brought material back. Yeah, and it's like, I remember when we were talking about going to the moon several years ago, and a lot of the public that I would talk to would say, well, we've been to the moon. We know everything about the moon. And I'm like, well, okay, if you got a bag of rocks in Florida, and you got a bag of rocks in Arizona, and maybe some from Maine, would you know all about the surface of the Earth? Like, well, no. Well, that's basically what we have. So we don't have the capability, or did not have the capability, to move around the lunar surface. We couldn't use something like a drone. Well, then we didn't have drones. But even if we had drones, there's not enough atmosphere or anything like that. One of the most valuable things that we have found on the lunar surface in my career is water ice. Finally, it's mostly at the poles. Coldest places in our solar system are the poles of the lunar surface, and a lot of that water ice is deposited by comets. But the sun never shines down into them. So whatever lands in there stays in there. And with water ice, you can make fuel. And so you can send a hopper. Something that you can manufacture your own fuel from that water ice, hop it over to some spot on the moon, hop back, refuel, hop to another spot. You can actually begin to explore the moon much more thoroughly that way. I'd love to see that.
You've been doing this outreach for quite a number of years, and I'm wondering early on how much pushback you got from people who had read and enjoyed the Andromeda Strain.
Oh, yeah. I love that movie too. So it was, I've watched that movie probably 3 times. And one of the things that we have hopefully gotten good at is containing samples. We don't just contain samples, we contain astronauts. We contain, we study them before we let them back out in public. And we also study, we also don't want to harm the planetary surfaces either. We have offices that study that. And it's like, okay, what are we adding to this? How do we deplete? For instance, when we slam into Didymos B, we will do everything we can do to completely deplete every bit of fuel on that spacecraft before we hit it, because we don't want to contaminate it either. Because we don't know what we might could learn later, but it may be useless to it if we contaminate it. So we actually spend quite a bit of effort and time and planning to not only not contaminate the samples when we bring them back, but not contaminate the rest of the body there. So it's not something that we just do willy-nilly at all. Now, the environmental strain, that would be fascinating though, wouldn't it? So something that replicates that fast. Anyway, I've got time for other questions if anybody's got any. Yes.
So I read up a little on, I'll just say 65803.
Mm-hmm.
65803. It was discovered in 2003. How come they didn't choose any other asteroid?
There were other candidates, and what we do when we choose a target, there are panels, there are other targets that are discussed, and it's like, well, is this in the size range that we could probably affect? Is this something that we can get to in a reasonable amount of time? How's the surface? Does it spin? You know, which direction does it spin? There's so many things that you consider on these before you actually determine what you're going to or where you're going. And often you don't check all the boxes. This is the one that checks the most boxes, so this is what we're going to try. So I don't know how many were considered, but I'm certain that several were.
Just curious.
Mm-hmm.
Which other candidates there were
Yeah,
for future launches that
exactly.
come about?
Yep. Or do we find more? Maybe we'll learn a little more about this one and find out that it's there's something that we could have done different, and we can open it up to more candidates. So, you had a question?
No.
Oh, I thought you did this. Yes, sir.
What other options for planetary defense do we have?
What other options? So far, this is our best option. You know, I've heard other foreign entities talk about nuclear options and things like that, and I'm like, ooh boy, I don't want to go there. I'd much rather have the capability of detecting these early and nudging them out of the way than to just go out there and try to obliterate something and make this spectacular light show as pieces of it come into our solar system and pieces of it come into our atmosphere. Maybe not pieces large enough to hurt anything, but still, I think probably the best plan that I can see is focus on early detection with some mitigation, and that's one of those missions that we were talking about. That's what it's out there for, and maybe we need more of those. You know, more things that are looking out there and can detect these things quicker. Sir.
I have a question that's theoretical.
Mm-hmm.
Let's say an asteroid is within visibility of hitting Earth. Would NASA be able to stop it right now?
Oh, wow. How far away is it? How much time do we have?
Let's say it's with the best telescope we have.
And we can project that it's going to come and impact the Earth. I mean, if it's the size of the Empire State Building or bigger, probably not a lot. Not a lot of options.
Dark wouldn't do it.
Oh no. Not even close. You know, we're going to hit something that's, well, it's several times bigger than a bus, but it's not.
Would we have to do some type of nuclear at that
If it was that desperate, then, you know, I would think that, and it's not all up to the United States either. You're going to have other countries with great ideas, and they're going to do their thing as well. Hopefully we could work together, you know, because that would be the quickest way to do it, is if we pulled our resources I mean, just like on TV, everybody pools their resources. You gotta say, well, I've got something ready to go that'll make it, but I don't have a payload that we could use to do that with. I kind of doubt that we're gonna have oil rig drillers, you know, and stuff like that up there, but there are ideas out there. And to the level of desperation that we were in, would probably dictate the level of how aggressively we would have to respond.
So right now, we don't have the capabilities.
We do not have the proven capability. Okay, I would put it that way, because we've not ever done it. This is one thing that will hopefully give us some proven capability, and then we can extrapolate more data from that and say, okay, if it was bigger, what could we use? How fast would we have to be going? How much mass would we have to have? Where do we want to push it? You know, you want to push it into another one, maybe? Something like that. Of course, when you start playing pinball out there, you don't know what you're going to get. So it's complicated. Yeah. I don't think that answered your question fully, but there's a lot of variables that would go into answering that question. Yeah. Sir?
That does bring up an interesting question of whether there's an international system set up for planetary defense, you know, because you did say that the U.S. is just only one.
An international system, I'm not aware of. Independent systems, yes. I had read something, it was probably some very reputable source like Facebook, about some Russian plans, that they had been thinking about this for a while and were wanting to work on it, and they had some unique ideas. So again, I'd like to see more collaboration there. I'd like to see more early detection, things out there, not just ground-based telescopes. You know, things that we're not very good at seeing things coming from the sun. You know, so it would be nice to be able to set something up to where we could see that. You know, sometimes we only have about a month's warning and something flies past us at a few 100,000 miles, and those are scary. Sure.
So besides asteroids, what other planetary defense things should be considered?
Well, I mean, that's the biggie, but then again, comets are potentially dangerous as well. I mean, you're looking at one of the theories, what is it, Tunguska in Siberia, where all that damage was done a little over 100 years ago. And they're saying that was more than likely a comet that heated up so much that it never actually touched the surface, but it heated up so much that it got close enough to the planet and so hot that it just blew up into a piece of steam and was several times bigger than most of the nuclear explosions that we've been able to produce. If it had been on the surface when it happened, it would have been a whole lot worse. So, yeah, comets. Comets, not good either. Yep. Is that everything? Nobody wants to know how to pee in space? All right. I'm sorry. Yes.
I'm kind of a visual person, and I'm thinking like a map. Like, here's Earth, and now they're going to send off this rocket to someplace to hit to do this dark mission. Do you have in your presentation anything that's a visual of, well, what's the path? What are we going past? And
Actually, I do. Let me see if I can pull it up. Oddly enough, yeah, I'll probably say that. I might have changed something. All right, can we see that? All right, that's not huge. But that does give you an idea of how big Didymos B is. It's just a little taller than the Statue of Liberty, and probably in mass close to the size of the Great Pyramid of Giza. But let me see if I can find the chart you're interested in. The actual trajectory from Earth itself. I mean, that's part of the trajectory, but that's not the one you're looking for. I know it's in here. This is a lot of charts. Do what? Brian Day is doing one, I believe, tomorrow or later this afternoon. I've got the schedule in my pocket.
From 3:30 to 4:30, the Italian space agency's in the same room.
Okay, they'll be doing a different one.
A hard rain's gonna fall, projecting Earth from killer asteroids. That's Brian Day. It's actually in C40.
Okay. Some of those are just spooky, aren't they?
And that's at 4:30 to 5:30 today. Okay.
Some of those are just spooky, and I don't want people to leave here, scared to death about this, because, I'm pretty lucky so far. We do have a lot of we have a lot of strikes. In fact, hang on a second. There's a really good chart in here. That one. Those are trackable impacts that we've had recently. I say recently, from 88 to 2019. So they happen, folks. Oh, sure. Yeah, sure. They happen. Yeah. Mm-hmm. That's still not that chart you're looking for. Oh, sorry. They're fireballs. They're fireballs, whether they actually impacted the surface or not. Right. But, I mean, you can see something the size of a grain of sand. But these were more substantive than those little grains of sand. These weren't just tiny little streaks. These were fireballs, coming across. So more than likely there's pieces of these somewhere. And that's a lot. Be glad we have such a thick atmosphere.
Is that a temperature chart on the right?
It is. I'm gonna have to. Impact energy. Mm-hmm. Yeah, the energy that it would have impacted at. And see, there's Tunguska, the big red one. Yeah, up there. That was 1908. 5 megatons of TNT.
That was when?
1908.
Oh, 1908.
Mm-hmm.
That's how much energy it produced.
Right.
Wow.
And again, that was an air burst. It didn't hit the surface. Mm-mm. It right. And that's a good thing. I'm sorry.
Do you have a similar chart of ones that landed?
Not in this presentation.
Oh, okay. Would it be more dense than that?
If you count up all the little tiny ones and stuff, yeah. I mean, it would be. I mean, I'm wearing one. My wedding ring is it's gold. It's a ring of asteroid, and then it's got a stone for every planet. I'm a nerd. I am a nerd. Yeah. No, it's not. But it was made in California. Yeah. And I have a nerdy tattoo we won't go into. But it's yeah. I mean, they're actually more common than you think. I know people. If you walk over to the exhibit area, you can pick up one about that big over there. They're nickel iron. They're very heavy. Yeah, you should try that. Mm-hmm. fact, that's where I'm going as soon as this is over. Sir. Mm-hmm. That Mars what? I'm sorry? Oh, right. That drone hasn't left yet, but we did land another rover this year. Nice big rover too, and it's working great. We're pretty good at rovers now, actually. And there's actually there's a pattern to the way we do things. It's not talked about very often, but there's a pattern to the way we do things. I mean, we do Earth-based observations, we do spacecraft-based observations, and then we may land. And then the next one would be land and explore, and which that's what I'm saying. The moon is one of those places that the only way we've been able to explore it is by people in rovers, and there are some mechanical rovers, some robotic rovers being developed by other countries right now to study the lunar surface, which I think is a great idea. We sort of stepped out of our routine, and I think a lot of that was politically driven at the time. Who's going to be the first person on the moon? Who's going to put boots on the moon? Should we have done it the other way? We did send landers, but we didn't send rovers. We probably should have sent rovers. We had a couple of near misses on landings because we did not know enough about the surface. We were down to like bingo fuel on a couple of things, and you got astronauts saying, "Nope, we're not landing there. I'm taking over manual control and putting it down someplace safe." Whereas now we with the LRO mission, we've got 90% of the surface mapped down to the tabletop. So we can do a lot better now. I hope. Anyway, is there any other questions? Well, great. Thanks for letting me be here. I'm sorry.
For like human space exploration,
Mm-hmm.
what missions do we have in store for that?
Well, I mean, we've got humans in space right now, but as far as going to other planets or Mars, something like that, late 2020s, early 3030s. I'm just guessing because we've got new technology that we're trying to develop. Our first launch of the SLS is less than a year away, and we get that up and running, then that gives us a truck to go other places in. So it'll speed things up when we get that done. But anyway, great being here. Love this place. Thanks for letting me talk to you. And I'll be back tomorrow at some point.